Thank you for joining us to this installment of the CGGC seminar. Today we have Duygu Ceylan, which is a senior research scientist at Adobe Research. She has obtained a PhD from EPFL and the subdivision of Professor Mark Pauli. She is interested in machine learning techniques to infer and analyze 3D information from images and videos. She has specifically focused on 3D inference and analysis, both for man-made objects as well as humans. And she's excited to work at the intersection of computer vision and graphics, where she is eager to develop methods to bridge the gap between 2D and 3D. And on a more personal note, I'll say that I've seen her papers and that was always interesting and exciting. So, Ceylan, go ahead. Duygu, go ahead.
Yeah, thank you. Thanks a lot, Miri, for the introduction, and thank you for the invitation. So it's great to be here and share some of my research. So today I will be talking about my work in the area of 3D perception from 2D content and how this could be useful for some creative workflows, specifically for Adobe. So yeah, my research, as Miri also briefly mentioned, focuses on inferring 3D information from 2D content, which could be images, videos, or sketches. And I'm particularly interested in understanding, one, what humans are doing. For example, here we see a man standing, our physical environment. So we see like some tables, several chairs, and then finally how humans interact with each other and the physical spaces. So we see that this woman is sitting on the chair. So why is this important? Why do we want to acquire this 3D perception? Well, I think this serves two main purposes. First of all, if we have a good understanding of 3D, it enables us to build intuitive 3D workflows. So instead of dealing with low-level processing, we can build interfaces that enables easy creation of 3D content and customization. And second of all, this 3D information can also help us to empower 2D workflows themselves. For example, we can enable some editing operations that are 3D aware and would otherwise be very difficult to achieve. So with this motivation, I'm also particularly interested in answering several research questions through my work. Of course, there are many ways to represent 3D information. So the first question is, what type of 3D representations are suitable for different applications? Second of all, 3D perception from 2D content is usually an ill-posed and challenging problem. So one has to explore some priors to make this more tractable. So that's why another important question to ask is, what type of 3D priors can we explore, again, based on the different applications we are focusing on. And finally, our observations are usually limited. Sometimes we have just a single image or a sketch. So it's important to be able to see through occlusions and make up for the missing information. So that is the final question I'm interested in answering. So before diving into some research work, I would like to first give you several applications that we have built at Adobe in the several years and how these different questions come into play. So here is first application. So imagine you are a product, you want to design a product catalog, let's say for a mug, and you already have some 3D mug that you found from a database, but you want to customize this mug. Maybe you want to make it a little bit taller. You might want to change the position of the handle and so on. So you want to make such edits. So what we did here was to build this 3D interface where you can specify such edits in a more high-level manner instead of directly going and editing like the actual vertices or the triangles. So in terms of representation, we have focused on 3D feature curves because these are pretty characteristic for man-made objects. We have also used priors such as symmetry, planarity, or orthogonality, so that if you make some local edit, it can propagate to the rest of the model in an intuitive way, even without the user noticing. Here is another application scenario. So let's say you have an input video of a person doing some motion and you want to retarget this motion to a 2D or a 3D puppet. So in order to empower this application as the underlying representation, because we are really interested in human motion itself, this time we are using skeleton-based representations. And since monocular motion capture is a hard problem, we also had to utilize some priors. So in this case, we are using human motion priors. Basically, given a large data set of plausible human motions, can we learn that space of what a plausible human motion is, so that our predictions are always within that space? And having this prior also helps us to reason about occlusions. From a single video, there will be times where the person is self-occluding, or there might be other occlusions. But if we can project our predictions to the space of plausible human motions, we can always complete our motion estimations. Another application where human pose comes in handy is actually for image search. So let's say you have a large database of images like Adobe Stock, and you are interested in looking for some images of people with a specific posture. So it might be very difficult to explain what you are looking for in words. So here we are using the pose itself as our feature query. So since it's still about human posture and pose, we are using, again, a skeleton-based representation. And similar to the previous application, we are making use of human pose priors in this case, so that you might have many images where only the upper body of the person is visible, but using such priors, you can try to hallucinate what the lower body configuration could be, so that you always have a complete feature to do your search task. And the final application is for image editing, specifically 3D aware editing of human faces. So what we do here is, given an input image of a person, we try to predict the shape of the 3D face and use this information to rotate the face as if you're rotating it in 3D. Since we are looking at specifically faces, we have good deformable template models to represent the 3D information. And similarly, there are also good statistical priors about what a human face looks like. So we make use of such priors to make this more robust and accurate. So yeah, these are just some quick applications that I wanted to demonstrate how this 3D perception can be useful. And with that, just like a brief summary of my research, as I mentioned, I'm really interested in understanding what humans are doing, understand about our physical spaces, scenes, and objects, and finally the interaction between the two. And today I will be talking about two specific research projects in this space, one focusing on garment design and the other one more general single view reconstruction. So yeah, with that, let's first start with the first project. So here our goal was to be able to build an intuitive design system to help designers design garments. So before I go into what we specifically did in the project, I would like to first introduce you what a traditional garment design workflow looks like. So usually the designer starts with some initial sketch. So this sketch really conveys like the final look of the garment you want to achieve. And then given this concept sketch in mind, the designer has to start designing the 2D garment patterns and also look into how they drape in 3D. And as you can imagine, this is not an easy task. So usually one has to go back and forth between adjusting the pattern parameters and then looking at them in 3D. So the goal in this project basically was to be able to replace this iterative workflow with a more automatic 2D and 3D workflow. So what do we want to do? So specifically given an input sketch of a garment, we want to build a system that can automatically infer the parameters of the garment patterns, as well as how the garment would look like in 3D. So given such predictions, the designer can go and either make some changes to the patterns themselves or go and edit the sketch directly, and the system can update its predictions, so we get the updated design. Once you are satisfied with the design, because we have both the 2D and the 3D information of the garment, you can easily apply any texture pattern and see how it would drape in 3D, and also perform a final physical simulation to get the accurate draping of the garment. And one interesting problem usually in garment design is to be able to retarget the same garment design to different body shapes, such that the look and how it drapes is similar. So we also want our system to be able to support such retargeting workflows. So this is the system we want to build, and how can we build this system? So the first step was actually looking at this different operations in the workflow. It was important to identify the different design spaces one has to work with. So first there is the sketch design space. So through the sketches, you basically convey what the final garment should look like. Second, there is the parameter space that contains the parameters of your garment patterns, for example, the length of a sleeve, the length of a t-shirt, as well as the material parameters. And then there is also the parameters of the underlying 3D body shape. And finally, there is the 3D space where you look at how the garment drapes in 3D. So as you can see, this is really a problem with multimodal design spaces. And what we did in this work was to be able to train machine learning algorithms that can go from one design space to the other. So specifically, we train one network that goes from the input sketch to the draped 3D garment. So basically, from the input sketch, we predict how the garment would drape in 3D. We have another network that tries to predict the parameters of the garments from the input sketch. And finally, another network that takes the parameters as input and then predicts the 3D draped garments. And the key was to be able to train these three networks in a joint manner so that they actually learn a common latent space. So once you have this common latent space, now it becomes very easy to go from one design space to the other. So here is the system in action. So basically you start with some input sketch, and then the system predicts the garment parameters and how it drapes in 3D. As I said, because you have both the 2D and the 3D information, you can easily go and make changes to your texture patterns, and the 3D draped garment will be updated automatically. Here we start making some changes to the sketch. So maybe we want the sleeves to be a bit shorter, and then we want to add some additional fold lines and make the t-shirt a bit wider. Excuse me. And then the system automatically updates the prediction. So basically this was the original sketch, and then this is the update before and after. And then here is another edit. So basically you might want to add some additional fold lines to the front of the t-shirt, and then you see how those folds are now reflected automatically in 3D. This was before and after. So here are some additional examples where we use some reference images as input. So given the input images, we can try to infer the sketches from the images and provide them as provide them to our system, and the system can predict the 3D garments. So with many machine learning algorithms where you learn this latent space, one advantage is now you can also start traversing this latent space, and the changes in 3D will correspond to some smooth changes. So this in a way provides the designer with the fourth design space, the latent space. So in addition to dealing with sketches or the parameters, the designer can now also try to traverse the latent space to explore different variations of a garment. And as I mentioned in the beginning, retargeting is one common workflow in garment design. So here the goal is basically to be able to retarget the same garment type to different body shapes while preserving the look of it. So in this case, for example, if you look at the skirt and how the folds are in front of the skirt, they are more or less similar regardless of the body shape. So how would you do this? So to formulate the problem a little bit more, basically we have two different body shapes and we have already designed the garment for one of them. If we naively use the same garment parameters and then drape it on the new body shape, they will actually most probably look different. So the goal is to be able to find the new set of garment parameters such that when we drape it, it looks similar on the two different body shapes. Since we have learned our latent space, which is a continuous space, we cast this as an optimization problem in the latent space. So the goal is to find a vector in our latent space so that if we drape it on the new body shape, it will look similar. And here is some results. As you can see, given the single input sketch with different body shapes, we can automatically infer different sets of garment parameters so that the draping looks more similar across the different body shapes. So yeah, this was kind of like a quick summary of what we did in this work. So of course, where do we go from here? So one thing is when we were designing this system, we made the assumption that the body is always at some specific pose, like an A pose configuration. But of course, you really want to look at garments at different body poses to see how it really drapes as the human moves. So we showed some initial results in the paper, but I think the problem of how to simulate garments under different human motions is itself a big research area to explore. So recently we have been looking into this problem. So of course you can use physically based simulation methods to simulate the garments, but these are usually computationally expensive and also sometimes not very easy to set up so they can explode. So what we are trying to do is train machine learning algorithms that can take as input a coarse simulation and then on top of it simulate some plausible wrinkle details so that you don't have to go through the complex simulation process. And of course, the input can also be just a skinning-based animation, and one can try to enhance it with some plausible wrinkles. So this idea of using machine learning to approximate the simulation process is one area I'm exploring actively. So recently we have also looked into how to learn to simulate soft tissue dynamics. So here in this example, our input is this skinning-based animation of a 3D character. And then we also have some information about the material properties like the stiffness. So basically the red regions are less stiff, so we expect more soft tissue dynamics. And then given this as input, we train a neural network that can try to enhance the animation with such secondary dynamics. And the goal is, of course, to build a system that can generalize across different mesh topologies and so on. So yeah, with that, I want to now switch gears a little bit. So in this first part of the talk, we looked at garment design, and really the gist of it was to be able to come up with these garment templates and then predict their parameters. But of course, in a general 3D reconstruction problem, we cannot always assume we have good templates to start with. So what do we do in that case? So in the second project, I want to talk about what we did in a more like general single view reconstruction problem. So in this case, we are, as our 3D representations, we are using implicit functions. So just as a reminder, implicit functions are commonly used in graphics, and basically the idea is you define this function where it basically defines the distance from a point in 3D space to the underlying surface, and the sign of it can tell you whether you are inside or outside the surface. So the main advantage of implicit functions is, of course, they are model-free, so they are more generalizable across different object categories. And in theory, you can also say you can get infinite resolution, since you can sample this function as many points as you want. And the final advantage is that they're continuous. And this actually is very important because it turns out that they are very friendly for machine learning algorithms. So that's why we have seen a lot of excitement around learning implicit functions in the past few years. So one common workflow has been, so given some feature vector that represents your objects, so this feature vector z, and some sampled point xyz in the 3D space. Usually people train these multi-layer perceptrons that can extract some features from the point, and then given the features of the object, you try to predict the sign distance function of that point. So if we try to now apply this, I guess, naive logic to our task of single view 3D reconstruction, what we can do is replace that feature vector z with some features that we extract from our input image. So given the input image, we have an image encoder that gives us some image features. Then for every point in 3D space, we can extract some point features and then predict the sign distance value of that point. And if we do this for many sampled points, we can then use algorithms like marching cubes to basically reconstruct the 3D mesh. This seems reasonable, but of course, if you look at especially the back of the chair, it lacks a lot of details. And one main reason for this is the fact that for every sampled point, regardless of where the point is, we are just using the same set of global image features. This is good to capture the overall shape of the object, but it also lacks information about the local details. So how can we tackle this problem? So this was kind of the focus of our work. So if we can now predict some viewpoint information given the input image, basically for every 3D point that we sample, we can also project that point to our image space. And we can now start extracting some local image features around the neighborhood of the projected point. So what does this mean now? In addition to the global image features, for every point, we can also extract some different local image features and use both of these features to predict our sign distance value. So we took this idea one step further. So instead of training basically one network architecture that would combine all these features and predict the SDF, we tried to design a two two network architecture. So the first architecture is similar to what I described in the beginning. You extract your global features and then you make an SDF prediction, and then there is another branch that basically utilizes the local features and makes another SDF prediction. And you can combine the two to get your final prediction. So we can really think of this architecture as like a two-level approach. In the first branch, you try to reconstruct the overall shape of the object, and the second branch tries to add the details as a residual on top of that global shape. And here is what you get as output. As you can see, we start getting much more details compared to the previous version. So here are some additional examples. So given the same input image, the predictions just using global image features versus the predictions that uses both global and local features. And we, in the second example, especially, you can see that we can even reconstruct the holes pretty well. One other advantage of this kind of workflow is it's very easy to extend it to multiple images. So instead of extracting features just from a single image, we can extract features from multiple given images and then do some averaging. And as you can imagine, as you add more images, the quality of your reconstructions can increase. So yeah, this was basically the gist of this work, and of course there are also many exciting directions to explore more. So I would like to talk about these future directions by going back to the research questions we asked in the beginning. So the first question we asked was what type of 3D representations are suitable for different applications. So today I talked about two different works. One was using garment templates as our underlying representation. And there are many advantages of this type of model-based representations. So they are easy to control because you have a predefined parameter space to deal with. And most of the time, these parameters are also semantically meaningful. For example, here in this t-shirt example, you might have one parameter that corresponds to the length of the sleeve. And another advantage is if you use the same set of template to represent different instances of the object, you also get correspondences across them for free. On the downside, these templates are topology dependent, so it's not very easy to come up with one template that can represent different topologies. And also sometimes they may not be suitable to capture very fine scale details. In the second project, we talked about implicit representations. I guess the main advantage of these representations are, one, they are very easy to adapt to different topologies. They are not topology dependent, and also they are friendly in terms of capturing the details. And I guess mainly for these two reasons, we have seen a lot of work in this field. So in our work, we were predicting the sign distance field, but there might be other follow-ups. For example, one can also try to reconstruct both the geometry, but also the texture. So basically for every sampled point, you can also predict an RGB value. You can predict some implicit neural features, which you can maybe combine with a neural renderer to render the final images. And also, I guess the recent line of work around nerves is to be able to predict the reflectance field for every point. These are all advantages of these representations, but I guess on the downside, they are not as easy to interpret as having an explicit template model. So in short, both model-free and model-based and implicit representations have their pros and cons. So I think as a future direction, it would be interesting to look into how can we build systems that utilize hybrid representations. There are some recent work looking into this problem. For example, one, I guess, good problem domain is reconstructing humans. For the underlying body, we have good deformable template models, but on top of that, adding garment details might require maybe more implicit type of representation. So it's interesting to combine the two. Another problem domain where this type of hybrid representations would be useful is, I guess, human-scene interaction. Again, for humans, we could utilize some good template models, but the scene itself might be very generic and not easy to represent with templates, and also interactions themselves might benefit more from implicit representation. So in some ongoing work, we are looking basically into how to represent such human-scene interactions. Another question we asked in the beginning was what type of 3D priors to explore. And for the model-based representations, usually because you have a predefined set of parameters, one can learn some statistical priors, either through like neural network type of approaches or more classical PCA type of approaches. So moving forward, I guess another important question is how to utilize some 3D priors for implicit representations. I think, again, humans, like human faces or human bodies, might be a good problem domain to explore this. We do have good deformable models both for faces and bodies. So it might be interesting to see if we can first learn some generic implicit representations, but then on top of that, utilize the power of implicit representations to capture more details, for example, to add person-specific features. So this would be another thing I'm excited to explore. And finally, the last question was how to see true occlusions. In the two works I've described, we didn't really have any explicit way to model occlusions, so we just expected the networks to learn this from data. For example, if you are trying to reconstruct chairs, even from a single image, because you learn how chairs look like through your training data, the network is able to do a decent job. But I think it's interesting to see if we can provide more explicit cues to reason about occlusions. So for example, let's look at this video. There are multiple people doing the similar dance. They are not perfectly synchronized, but just by looking at the people in the front row, we already have a pretty good idea of what this person in the back was doing, even though we didn't observe her in most of the video footage. So it's interesting, for example, to see if we can use such weak cues to reason about motion of humans, even though they're not truly visible in our observations. Similarly, if you look at this input image, we don't really see how the lower body of this person looks like, but because she is sitting on the chair, I guess we all have good ways to complete that missing information. So looking into these human scene interactions and using that to improve our predictions about both the scenes themselves, but also the humans is another direction I would like to explore more. So yeah, this basically is kind of concludes the research part of my talk. Before I end and take questions, I also wanted to, I guess, do some shameless advertisements. Just briefly describe you what Adobe Research is doing and maybe get your attention. So Adobe Research has different offices across the world. So we do, of course, have many offices in the US. We recently opened a new office in Europe, in London, and then we have another lab in India. So we do a lot of work in many different areas in graphics, vision, machine learning, and data science. And we do publish in many different conferences in these fields. And most of these publications are actually through our internships and academic collaborations. So every year we have many interns come in, work with us, and we continue our collaborations with them until we basically complete the projects and can publish it. And this is one picture from a retreat from the days where we could still get together and do nice social activities. So we are currently in the internship application season and also having full-time hires. So if you're interested, feel free to visit our website or drop me a note, and I'll be happy to chat more. And yeah, with that, I want to stop here, and if you have any questions, happy to answer them.